So we're going to look at this problem, which is the first in a series of problems of this type where actual calculations will be done. So in this first one, it gives you some information about the size of the vessel, 10.0 liters, the moles of SO2, the moles of O2 that reacts, and the moles of SO3 that appears at equilibrium. And the question is asking for the Kc, and it gives you the balance equation here. Let me just say from the outset that the 1000 Kelvin here doesn't really matter because it basically is giving you the temperature conditions for the reaction, but it will not be involved in terms of the calculations because typically when Kc expressions are given or Kc values are given, they typically provide a temperature just to indicate or reiterate the point that the Kc value is dependent on the temperature. So once the temperature is fixed, the Kc value remains the same. All right, so let me go to here. So as you can see, I've copied and pasted the question here. I've written down the balance equation here. So whenever you're dealing with a problem of this type, we have to set up what is known as an ICE table. ICE stands for initial, change, and then equilibrium, right? So initially, before we even do that, we need to determine the concentrations of the SO2 and the O2. So let me do that first. So the concentration of SO2 is equal to 0.2.250 moles divided by 10.0 liters. And this works out to be equal to 0.0250 M. And we do the same thing for the oxygen. So the concentration of the oxygen is equal to 0.200 moles divided by 10.0 liters. And this works out to be equal to 0.0200 M. Now remember, these are the initial values, initial concentrations, right? According to the question. So as far as the SO3 is concerned, the concentration of SO3 is equal to 0.162 divided by mole divided by 10.0 liters. So this works out to be equal to 0.0162 M. All right. So just draw a dividing line here so as to avoid confusion. Initially, we will have 0.0250 M of SO2 and 0.0200 M of O2 and none of this initially. We're going to have some changes in these amounts, which I will get to later, but I want to get to the equilibrium part of it. Now at equilibrium, according to the question, according to our calculations, the concentration of SO3 will be 0.0, decimal point here, 0.0162. So that will occupy, let me just draw some lines here and here. Okay, so that will occupy, that value will occupy this position right here, 0.0162, all right, M. Okay, so the key thing is to determine the values that you're going to represent here as the changes. Well, we can easily determine the change for the SO3 because we started off with 0 here and we ended up with 0.0162 here. So therefore, as far as the SO3 is concerned, the change here is plus 0.0162 M, all right? So that's easy. Now, based on this change here, we can determine the changes for the SO2 here and the O2 here. How do we know that? Because of the balance equation, and more particularly, because of the coefficients of the different substances. There's a one here involved in the equilibrium system. So if the change for SO3 is plus 0.0162 and there's a 2 to 2 mole ratio between SO2 and SO3, that means that the change here for the SO2 would be minus 0.0162 m. Of course, it's minus because the SO2 is reacting to form this amount of SO3. In the case of the O2, there's a 1 to 2 mole ratio between the O2 and the SO3. So therefore, the change as far as the O2 is concerned is minus half of this value, which would be 0.0100 m. All right? So therefore, to get the equilibrium concentrations of SO2 and O2, all we have to do is add the initial amounts to the changes. So in the case of SO2, it's 0.025 minus 0.0162. And according to my calculations, this works out to be equal to 8.8. Oh, 1 minute. 8.80 times 10 to the minus 3. So that value would go right here. 8.80 times 10 to the minus 3. And then as far as the oxygen is concerned, that's easy to do because it's 0.0200 minus 0.0100. So that would be 0.0100 m. All right. So these would be the values at equilibrium. So therefore, to find Kc, the Kc expression would have to be written for this equation, which is concentration of SO3 squared divided by concentration of SO2 squared times concentration of O2. So we put the concentration of SO3 squared up top, 0.0162 squared divided by SO2, which is 8.80 times 10 to the minus 3 squared. Make sure I put a decimal point here. And then times O2, which is 0.0162. All right. So all I did was plug in the equilibrium values here, here, and that one into this equation. And I'm going to do my computation now. 0.0162 squared divided by 8.8 times 10 to the minus 3 squared divided by 0.0162. So according to my calculations, this works out to be equal to 209. So the Kc value here is equal to 209. And again, don't need to worry about any units for Kc, as I said before. All right. Okay, so that's it for this example. So the next example will be done in the next video coming up.